Hello and welcome to Empowered Learning. This video will be about discussing the commutative and associative properties for multiplication and addition. We will also talk about what we mean when we talk about an additive inverse as well as a multiplicative inverse, and we will discuss the distributive property. In higher mathematics, all of these items that we're talking about is what's a part of what we call an abelian group. For those of you who haven't studied higher mathematics, and particularly modern algebra, you may not recognize that term, but you do recognize things such as we know that 1 plus 2 is the same thing as 2 plus 1. And we also know that 3 times 2 is the same as 2 times 3. Well, it turns out that in mathematical structures, it is not always a given that that is true. Whenever we are working within the real numbers with the simple operations of multiplication and division, we know that commutative property of addition and multiplication are true. We also know the associative property. So an example of that would be, we know that 1 plus 2, and then after all that, if we wanted to add 3 to it, that would end up being 6, will be the same as if we wanted to add 2 plus 3, and then after that we add 1. So I'm going to go ahead and write that so that you can see what that would look like. Okay, so looking here, if we said 1 plus 2, and then we did that first and did plus 3 after that, that would be the same as saying 1 plus, and then we did 2 plus 3, like that. So both ways, you see that we end up getting 6. But it's just the order in which we do it first. So that would be what the associative property of addition would be. And so to kind of go through these rules here, just like how I was saying before with the commutative property of addition, we know, for instance, that 2 plus 1 is the same thing as 1 plus 2. In both of those cases, we have 3. We also know that here 3 times 2 is the same thing as 2 times 3. So that's an example of that. Of course, with the associative property, we already seen one with addition. For subtraction, I'm sorry, not subtraction, but the multiplication, we would say that 1 times 2, and if we did that together first and then multiplied 3, of course, that would end up being 6. And that would be the same thing as saying just 1 times and then doing 2 times 3 first. And so let me erase that and do that again. And of course that would equal 6 as well. So that is where the commutative and associative properties for addition and multiplication come in. Alright, so if we get some practice in, we want to use either the commutative or associative property to complete this. So we know that x plus 8 will be the same thing as 8 plus x. And we know that 7 times x will be the same thing as x times 7. And in this case, we're using the commutative property of addition, whereas here we're using the commutative property of multiplication. And of course for C, we know that 3 plus 8 plus 1 is the same thing as saying 3 plus 8, doing that first, and then afterwards adding 1 to that. And of course this is the associative property of addition. And similarly for D, we know that this will be the same as if we were going to multiply 4 and 2 first, and then after that multiply a negative 5. And this is the associative property for multiplication. And then when we have two letters written together like how we see here, this is implied multiplication. So we could do this first. Oh, sorry, let me not write it like that. Try to keep it in line with what we're doing here. We could write it like this and say that x times, and then we have y times 18 in parentheses first is the same thing as xy, and then multiply that times 18. And this is the associative property of multiplication again. So those are examples there. Alright, so now we want to talk about additive and multiplicative inverses. You've probably heard of additive and multiplicative inverses before, you just probably have not called them that. So for instance, when we talk about an additive inverse is nothing more than the opposite of a number. And most of you have heard of the opposite of a number. So for instance, if we wanted to say 2, what is the opposite of 2? Most of you would say what? Yep, that's right. It would be a negative 2, right? And let's see, my cursor is kind of acting up here. That would be a negative 2. So let's say if we had a negative 18 here, what would the opposite for negative 18 be? And you're right, again, it would be 18. So that is what an additive inverse actually is. That's just the proper name for it. The reason why we call it that is because anytime we take a number and we add it to its opposite and we get 0 as its result, then these two numbers that we're talking about are additive inverses of each other. Okay? Or if you want to give it the mathematical slang vernacular to it, it will be opposites. So the multiplicative inverse kind of works the same way. So here we know that, let's say if I take 2 and if I multiply it times 1/2, that would give me a value of 1. And same thing happens if I take 4 and then I multiply that times 1/4, I would still get 1 as an answer there. So 2 and 1/2 are multiplicative inverses of one another, and 4 and 1/4 are multiplicative inverses of each other. What you're used to calling a multiplicative inverse, this is actually what is called a reciprocal. So whenever you hear the word reciprocal, that actually means multiplicative inverse. And when most people learn about reciprocals, they learn that the reciprocal is just whatever the number is, you flip it. So for instance, if I wanted to know what is the reciprocal of -5, then you're thinking about this as if it's -5 divided by 1, and if you flip that number, then you get -1/5. Similarly, if we were talking about, let's say, the number 82, and we wanted to figure out what is the reciprocal or the multiplicative inverse of 82, of course, we are interpreting that to be 82 over 1, so the reciprocal of that would be 1 over 82. If we had a fraction example, let's say we had something like 7/8 here, and let's make it negative. Then the reciprocal or multiplicative inverse of -7/8 would be a -8 over 7, okay, or -8/7. And so essentially that is what additive and multiplicative inverses are. They are just the opposite of a number or the reciprocal of a number. You probably learned it that way before you started calling them additive and multiplicative inverses. Alright, so now let's talk about the distributive property of multiplication over addition. And so we just know here that whenever we have a situation, and I'll do a quick example here. So let's say we had something like 2 times, and then within here we have 4 plus 3. Then of course one way that we could actually do this is by order of operation, and we could say that this is 2 times 7, and then 2 times 7 is 14. But we could also do this another way by distributing the 2 over addition on the 4 and the 3. And if we did it that way, then it would turn out to be 2 times 4 plus 2 times 3. And of course here we know that 2 times 4 is 8 and 2 times 3 is 6, which still gives us 14. Now, in this example, it's probably don't see what is the use in doing that. But what if we had something like this? So let's say if we had 2 times x plus 3. Well, since we don't know what x is, the most that we could do is take this 2 that's here and distribute it to both terms. And we say that we distribute distributive property of multiplication over addition. So we're doing multiplication over this addition sign. So here that's why we would have 2 times x here plus 2 times 3, which would give us just 2x plus 6. And so that's what we mean whenever we distribute multiplication over addition. Down below you see these other properties called the identity elements here. And so what we talked about when we were talking about multiplicative and additive inverses actually has something to do with this definition of an identity. And so in general, we know that 0 is the identity element for addition because 0 acts like a mirror with that operation. So anytime you add some number to 0, you just get itself. And so it sort of acts like a mirror. 1 acts the same way as 0 does in addition. So 1 acts the same way in multiplication as 0 acts in addition, because anytime you multiply any number times 1, you get that particular number back again. Okay, and so how all this is tied is that when we talked about an additive inverse, anytime we take a number and we add it to its opposite, or what we call its additive inverse here, see if I can write that again, then what you get as a result always is the identity element for that operation. So here 0 is the identity element for addition, and we know that negative a is going to be a multiplicative inverse, an additive inverse for a. And so anytime you take a number with its operation and do its inverse to it, you always get the identity element. And so again, this is why whenever we take some number and we multiply it times its reciprocal, or what we call its multiplicative inverse, we always get the identity element for multiplication, which in this case is just 1. So you see here in these examples, if we were using the distributive property, you see how this first answer ends up being 7x plus 28y, because essentially what we're doing here is we're distributing the 7 over to x and the 7 over to 4y. And of course, 7 times x is just 7x, 7 times 4 is 28, and 28 times y is 28y. Since we don't know what y is, we just have to keep it that way. Similarly, the same thing for example B here. 3 gets distributed to the negative 5, and 3 gets distributed to the positive 9z. So of course, you see how we write them both there. And then of course our final answer ends up being negative 15 plus 27z. And then for this last one here, whenever we have a group of terms that are inside a grouping symbol and we want to change the sign of them, what we do is we multiply them by a negative 1. And whenever we just have a negative sign out here, like how you see, that's equivalent to that. So here we just distribute our understood negative 1 to all 3 terms, and then you see once we do all the multiplication over the addition, then all the terms have changed. So 8 was positive, now it's negative. X was positive here, now it's a negative term, and then W was a negative term, now it is a positive term. Alright, so now what we're going to do is do some more practice here just to make sure that we have this. So we'll start off with this first example here. And so we know that we're going to distribute the 5 over both terms there. So this ends up being 5y minus 20, since 5 times 4 is 20. For our next example, we just distribute our -4 over both terms, and a -4 times y is a -4y, and a -4 times a -6 is a +24. So we end up with a -4y plus 24 as our answer. For example C, we notice here that again we're just distributing -5 to all three terms, and we see that the first term ends up looking like this, second term like this, third term like that. And we have a -5 plus a +2x is a -10x. A -3y times a -5 is a +15y. And we have a -5 times a +6 ends up being a -30. And so this is what our final answer ends up looking like. So let's move on to examples D through G. So for our first example here, D, we see that we just have the negative on the outside. So essentially to us, all that means is that we're going to distribute this understood -1 that's here. So when you see this, you're literally just looking at this as if it is a -1 being multiplied by everything. And let me get rid of that and try this again. So looks like this, and now you will distribute to all three terms. And essentially what it does is it just changes the sign of each term that you have, because of course a negative times a positive is a negative, and a negative times a negative is a positive, and a negative times a positive is a negative. Okay, so for example E, we're going to distribute the 5 to both terms here, and for this we understand this to be plus an understood -1, and we're going to distribute that to both terms. So when we do this, then we know that the first two terms ends up being 5x plus 10, and then of course for the second two we have a -1 times a +3x, which is a -3x, and we have a -1 times a -4, which is a +4. And then of course from there we can combine like terms. We know that 5x and -3x are like terms, so 5 minus 3 is 2, so we're left with 2x there. And of course 10 and 4 are like terms, so 10 plus 4 is 14. And that is final answer on that. For example F, you can see sort of the same thing. The one thing that's different now is that in addition to us having a subtraction sign here, we also have our first term inside of our second term that's grouped that is negative as well, so we have to watch that. So for our first term here, we just get a -8x. Second term we get a +12, because a negative times a negative is a positive. And for our next two terms, we know a negative times a negative is a positive, so that's why we get a +2x, and then negative times a positive is a negative, so that's why we get a -1. And then from here we just combine like terms. Alright, so for example G, same thing here, we just have fractions. So we're still going to distribute to the first two terms, and then distribute this understood -1/6 to the second two terms. So when we do this, our first term here, 1/3 times 7y is going to be 7/3 y, minus 1/3 times a -1 is just a -1/3. Then after that we have a -1/6 times a +4y, which is a -4/6y. And then we have a -1/6 times a -7, which is a +7/6. 7/6. Okay. And so one thing that we can note here is that 4 divided by 6 is going to be the same thing as 2 divided by 3. And we know that because we know that when we work this out, cursor's acting up here again, so let's try to get that. We know that that's 2 times 2 over 2 times 3, and these 2's reduce to 1, and all we have left is 2 times 1, which is 2, and we have 1 times 3, which is 3. So we could take this term that's here, and all of this would actually just be 2 over 3y. And so now that we have that, we can take 7/3 y minus 2/3 y, and we'll see that we end up with 5/3 y. Okay, so in other words, these two terms are like terms. We also know that here negative 1/3 and positive 7/6 are like terms, but we can't add these fractions until we have a like denominator. And so we know that 1/3 is the same as 2 over 6, because if we form an equivalent fraction, we know that 3 goes into 6 2 times, or put another way, 3 times 2 is 6. So since 3 goes into 6 2 times, then we say 2 times 1 is 2. And we're doing the same thing if you were trying to do that this way. So let's say you had 1. That's way too big. Let me erase that and try that again. So we have 1 divided by 3, same as whatever divided by 6. And let me try that one more time. Yeah, I wanted a little space here. And so now we know that I would have to multiply this by 1, but 1 will look like 2 over 2 in order to get 2/6. So saying all that to say is that this term here could actually look like a negative 2 over 6. So now that we have a negative 2 over 6 plus 7 over 6, our denominators will pretty much stay the same. And we know that since 2 is smaller than 7, our number here is just going to be positive, because we're essentially looking at it like this. Whenever we add that fraction here. And so we know that that's going to end up being positive 5 over 6. And so this is our final answer for G. And so this concludes the video on the commutative and associative properties for multiplication and addition, as well as the additive and multiplicative inverses, better known as opposites and reciprocals, and exercising the distributive property of multiplication over addition. If you like this video, please give me a thumbs up. Hope this has helped you out a lot, and check out some of my other videos. Please take care.